In the last analysis video, we solved exercise 12 for 1. So today let's start with 12 for 2, where we have to prove proposition 12 for 5. Let's first recall the statement of this proposition briefly. So in the statement, we had a metric space x comma d, a sequence xn, and a point L in X. If you see the actual statement of the proposition, you go back there, you will see that n starts from m, where m is some integer. I have, however, written 0 here. So that means my index starts from 0 instead of that m. Can I do that? Yes, I can do that. I can renumber or relabel the terms of a sequence without fundamentally altering the sequence. It's like there is a group of people where each person has a name, but you rename them. Okay, that does not change the group or the people. So it's like that. This will actually simplify our solution. So then what was the claim? The claim is that these two sentences are then logically equivalent. If any one of them is true, then so is the other. What are these sentences? L, this point L is a limit point of this sequence. That is one statement. Statement means sentence. And this is the second one, that there exists a subsequence x and j of the original sequence, where also j, say it starts from 0 and goes to infinity, which converges to that point L. If this is true, then this is true. And if this is true, then this is true. That is the claim, which now we will prove. We start the solution by proving the easier half of the claim. The entire claim has two halves. So in this half, we assume that the sequence xn has a subsequence xnj that converges to L. That means now we have to prove that then this L is a limit point of the original sequence. For that, we need an epsilon and n. We have chosen a positive real number epsilon and a natural number n. To prove that L is a limit point of xn, we have to show that there exists some integer. Integer means actually it will also be a natural number, say small n, which is greater than or equal to n, and such that the corresponding term of the sequence xn is close to L in the sense that its distance from L is less than or equal to epsilon. If we can show that, then by definition of limit points, L will be a limit point of xn. And now our hypothesis is that xnj converges to L. So that means for this epsilon, there will exist a natural number j0, j0, such that the distance between xnj and L is less than or equal to epsilon for all integers j greater than or equal to j0. So existence of this j0 comes only for epsilon and because xnj converges to L. This n does not play any role here, but next n will come. Now ni is greater than capital N for some I greater than or equal to j0. Why? Well, that's because this xnj is a subsequence of xn, and so by definition of subsequences, these superscripts, those nj's, form a subsequence of n, the sequence of natural numbers. And that is why this is a strictly increasing sequence and so has no upper bound in the set of real numbers. In particular, this capital N is also not an upper bound for these nj's. So there will be at least one I such that ni exceeds n. It becomes greater than n. That is clear. However, what is not immediately clear is why you are able to choose I greater than or equal to j0. Let's test it. Okay. Suppose you don't accept this. You say no, this is not okay. I will find no such I for which this will happen. Then what is the consequence of that? You are saying that there is no I of this type for which ni will exceed capital N. What does that mean? It means that for all such I, ni is less than or equal to n. Alright. Now besides these i's, what other i's do you have? Those i's which are less than j0. But because I anyway is itself a natural number, so the other i's are finite in number. Corresponding to them, only finitely many ni's are there. They are bounded above by something, namely, for example, the maximum of them, because there are only finitely many. Now, your reluctance to accept this has also made this capital N an upper bound for these ni's, where I is greater than or equal to j0. So, for this type of i's, n is an upper bound for the ni's, and for the other i's also there is an upper bound. So, that's how nj actually becomes a sequence which has an upper bound, but which goes against its nature because it does not have an upper bound. That is why this has to happen. You must have at least one I greater than or equal to j0 such that ni will exceed n. Okay. So now what is happening? You see, now you go back to the previous line. If j is a natural number greater than or equal to j0, then this happens. And now I is one such natural number. So that means you can put I here, and that's how you are getting this. The distance between xni and L is less than or equal to epsilon. So now what have you found actually? You have found that for this epsilon and for this n, there exists a level or a stage ni which is greater than that n, and such that the corresponding term of the sequence xn, corresponding to what? Corresponding to that ni which exceeds this n, such that this term is close to L in the sense that the distance between them is less than or equal to epsilon. This is what we wanted to show, right? That's what we said just now. And that's needed to prove that L is a limit point of xn. So we have one half of the proof. So we write the conclusion, hence L is a limit point of xn. Conversely, let L be a limit point of xn. Now we need to show that xn has a subsequence that converges to L. And if that subsequence is xnj, then we are seeking those nj's. And that is why we next write, we now define a subsequence nj of the sequence of natural numbers recursively as follows. Now I will write the definition. We first define n0, of course, because that's how a recursive definition starts. You first define the object which corresponds to 0, and then the actual recursive part comes. n0 by definition is the minimum of this set, namely the set of those natural numbers n such that the distance between xn and L is less than or equal to 1. And then, given these ni's which have already been defined, n0, n1 up to nj, say, for some natural number j, we next define nj plus 1. This one is also the minimum of a set which is the set of those natural numbers such that this time the distance between xn and L is less than or equal to 1 divided by j plus 2. And also additionally, this n needs to satisfy this inequality, that it is greater than the maximum of those previously defined ni's, or equivalently that it's greater than all of them. It might look quite complicated at first, but you will realize why this is the most natural way to do things, to define it. Let us first of all see if this definition is a legitimate recursive definition. Because what does a recursive definition require? It requires you to define the objects in such a way that first you define an object corresponding to 0 which is uniquely defined, and then given some objects that already have been defined, you define the next object uniquely in terms of them. Is that being satisfied by this definition? Let's see. N0 comes first, which is the minimum of this set. Does there even exist a minimum of this set? That is the first question. What is this set basically? Basically, it's the subset of n, because that's clear from the definition. It consists of some natural numbers which satisfy this inequality. Are there such natural numbers? Yes, there are. There is at least one n for which this inequality is true. Why? That is because in this part, in this converse part, the hypothesis is that L is a limit point of xn. So if you imagine 1 in place of epsilon and 0 in place of n and apply the definition of limit points, there exists at least one n which is greater than or equal to 0 and for which the distance between xn and L is at most this epsilon. So we know that this set is non-empty and it's a subset of n. Because n is a well-ordered set, so there will be a minimum element. So it not only exists, but because of this definition, it is unique also. There is only one minimum. So that's how we get a unique object corresponding to 0. Next, say these objects are given. So next we define nj plus 1 like this. What about this set? Now you have understood at least what to do here. Here also you need to just verify that this is a non-empty subset of n. That's it. Then a unique minimum exists because n is well ordered. Here n needs to satisfy this inequality and also this one. Okay. Does there exist such an n? Again, yes, because L is a limit point of xn. How? Well, you go back to the definition of limit points. We need this inequality to be true, say. Okay. And now your epsilon has this value, 1 divided by j plus 2. Can you find an n for which this inequality will be true? And additionally, that n has to exceed this thing. Yes. And that happens because L is a limit point of xn. So that means this set is also a non-empty subset of n and hence has a unique minimum. Note that this part of the definition depends on these things. So this is a legitimate recursive definition, and that way we really get a well-defined nj. That alone, however, does not tell us that this is a subsequence of this. Something else is also needed. So we write the reason here. It's clear that this recursive definition is well defined, and the reason is this: since L is a limit point of xn and n is well ordered. But just now I said that this alone does not tell us that nj is a subsequence of n. Why? What else is needed? The only thing that is clear from the above definition is that each nj is a natural number. But you look at this example, this is the sequence of natural numbers, right? 0, 1, 2, 3, 4, 5 and so on. Now you look at this sequence where each term is 1. So that means each term is a natural number. However, this is not a subsequence of this because it lacks that crucial property that it should be strictly increasing. That is not there. You can think of other sequences also where things will oscillate, say 1 0 1 0 1 0 like that. That also lacks that property, so that is not a subsequence of this. This, however, is the subsequence of the sequence of natural numbers. It's the sequence of even natural numbers. Here, however, the terms increase steadily. 0 is less than 2, 2 is less than 4. So we now need to see if this is an increasing sequence. Otherwise, we can't say that it's a subsequence of n. And so we won't really have a subsequence of xn if we use this nj's if this sequence lacks that increasing property. But luckily, of course, that property is there. So we straight away write, since nj plus 1 is greater than nj for all natural numbers j, so nj is a legitimate subsequence of n. I could not write the full word here because I ran out of space. But how is this true? Well, let's look at the definition. What is nj plus 1? Nj plus 1 is the minimum of this set. In particular, nj plus 1 is after all inside the set, right? It's an element of the set. So that means it needs to satisfy these conditions. You forget about this first inequality for a moment and see the second one. Nj plus 1 has to be greater than the maximum of all these things. So, in particular, it's greater than each one of them, and that is why in particular it is also greater than nj. So that's where it comes from. And because of this only now we can say that yes, hence xnj is a subsequence of xn. So now we just need to show that this really is a not just a subsequence of xn but one which converges to that point L. And for that we next note these inequalities. The distance between xnj and L is of course greater than or equal to 0, that's always the case. But it's also less than or equal to 1 divided by j plus 1. You go back to the recursive definition. There actually you have j plus 2 here, but that is for nj plus 1. If you have nj, then here we will have j plus 1. What is it that we are using here? Namely the fact that in the set for nj, if you apply the recursive definition, to define nj, say, in terms of the previous ni's, there in the inequality part you will have this 1 divided by j plus 1. Now because nj will be an element of that set, so this inequality will be true for nj, or if you want to say for xnj. However, what will happen if I take j equal to 0? Will things work? Yes, they need to, because otherwise my definition will be useless. What happens if I put n0 here? Then I should also put 0 here, right? That means in that case the inequality will become distance between x n0 and L is less than or equal to 1. Yes, that is true. You go to the definition of n0. n0 being the minimum of that set is itself also present in that set as an element. So the distance between x n0 and L needs to be less than or equal to 1. So that is also true. So by the squeeze test, you recall the squeeze test from limits of sequences of real numbers. The limit of this middle sequence is equal to 0. Don't get suddenly confused, okay? Here we are talking about this sequence which is a sequence of real numbers. These distances are real numbers after all. Otherwise these inequalities will not make sense. You can think of this middle term as a sequence of real numbers depending on the index j. And the terms of this sequence are trapped between the constant sequence 0 and the other sequence 1 divided by j plus 1. Because j varies from 0, so if you look carefully, this is nothing but the sequence 1 divided by n, where n is a positive integer. So it's your familiar sequence 1 over n, which you know from the very beginning that it converges to 0. The constant sequence also converges to 0. So by the squeeze test, this sequence of real numbers also converges to 0. But then by the definition of convergence of sequences in a metric space, the sequence xn j. Now this is not necessarily a sequence of real numbers. It is a sequence of points in that metric space X that converges to L with respect to the metric D, and it is a subsequence of our original sequence Xn, which now converges to L. This is what we wanted to show, right? So this is where the solution ends. Let's solve another one, exercise 3, where we have to prove lemma 12 for 7. And this is the statement of lemma 12 for 7, briefly written. Xn is a sequence in a metric space X, D, and Xn converges to some point X0. That means we have a convergent sequence. Then the claim is that it's then a Cauchy sequence also. The solution is pretty easy. Essentially, it's the same thing that we did back then when we proved the similar result for sequences of real numbers, that every convergent sequence is Cauchy. But anyway, let's see the solution. So we start by choosing a positive epsilon because it's given that our sequence Xn converges to X0. So for this epsilon, there exists a natural number n such that the distance between the term Xn and X0 is less than or equal to epsilon divided by 2. This epsilon divided by 2, in its place you can also write epsilon. Nothing will essentially change, but we do so to make things look good. That's just it. For all n greater than or equal to n. So then for any integers I and j greater than or equal to n, we consider the distance between xi and xj, the ith and jth term of our sequence. By triangle inequality, that is less than or equal to the distance between xi and L plus the distance between L and xj. So we bring in L using triangle inequality. Now because I and j are both greater than or equal to n, you can think of them in place of this n here. So that means for each one of them, this inequality will be true. So this is less than or equal to epsilon over 2, and so is this. And their sum is epsilon. It is to get this epsilon here that we chose epsilon over 2. If instead if you choose epsilon, you will just get 2 epsilon, that's it. But then what is it that you have shown? You have shown that for any epsilon there exists a stage n such that the distance between the ith and jth terms of our sequence after that stage, all such distances are less than or equal to epsilon. So that means Xn is a Cauchy sequence. That's it.